In this short video, we'll be looking at how to use pH curves to select a suitable acid-base indicator. And also, at the end, you should be able to describe how the endpoint can be found from pH titration curves. You'll also, at the end, be able to explain the significance of the half neutralization point. Here, I've taken some red cabbage and I've matched it up with some alcohol. And what I'm going to do now is test it in some sodium hydroxide and some nitric acid. You can see there in the sodium hydroxide it's gone green, and in the nitric acid it's gone red, and there's just the neutral juice from my red cabbage. So all natural plant pigments could potentially behave as indicators. There's two important things to notice at this point. First of all, the difference between equivalence point and the end point. The equivalence point is exactly the point in which the number of hydrogen ions is equal to the number of hydroxide ions, whereas the end point is the volume of acid or alkali added when the indicator just changes colour. So the end point is the volume of acid or alkali added. Now, unless you choose the right indicator, the equivalence point and the end point may not always give the same answer. An indicator is really a weak acid. So if we look at the indicator, the protonated form of the indicator is HN, and the indicator in base, having released its protons, it changes colour. Therefore, if we were to write an equilibrium expression for the indicator, at the point in which half of the indicator is dissociated, and that is what we call the end point of the indicator, then the concentration of the undissociated indicator is equal to the concentration of the dissociated indicator. And just as we did with weak acids, the concentration of those will then cancel out. And therefore, the pH at which an indicator is at its midpoint or its end point, K indicator, if we take pK of the indicator, that is the pH at which it changes colour. Methyl orange has a pKa or pK indicator of 3.7. If we look at the chart here, at about 3.7, it's peach. It's midway between its red and its orange colour, and it changes over 2 pH units. From red to yellow, this peach or orange colour is when it's changing. Starts to change at pH 3.7. Phenolphthalein, on the other hand, has a pK of 9.3. At 9.3, this is when you'll start to see the phenolphthalein changing from colourless to not really red, it's purple. Indicators are simply weak acids, and when they gain or lose protons, they change the colour, and this is because the delocalized electron system here absorbs light in the visible part of the spectrum. So methyl orange, when it accepts a proton, so here you can see the protonated form, here when it's behaved as an acid and given up its proton, in the protonated form it appears red. When it loses the proton in more alkaline solution, so bases remove the proton, it becomes yellow. So at pH below 3.2, you can see it's red. Above 4.4, it's actually yellow. Let's have a look at a video of that. In the video, I first of all add some nitric acid, so you can see that the methyl orange is pink at about pH 1.87. I then add some drops of sodium hydroxide, give it a quick stir, and the pH starts to rise. It's still acidic at about pH 2.49 there, you can see. Now adding a bit more sodium hydroxide, and you can see immediately it's gone yellow. And the pH is only 4.45. As you can see here, the pH was about 4, still quite acidic, when the methyl orange indicator changed from pink to yellow. So the end point is well before pH 7. Just to remind you, in acid, methyl orange is pink. In alkali, it's yellow. And the midpoint, which is a cross between pink and yellow, remember, is this peach colour here. Let's look at a phenolphthalein indicator. At pHs below 8.2, it's colourless. When it releases a proton in alkaline solution, it becomes pink. Let's have a look at a video of that. So here I have some phenolphthalein and some sodium hydroxide, and at the moment there's just water in there. pH is about 7. So I'm now about to add some sodium hydroxide. There's already phenolphthalein in, and as you can see, it goes pink. But as it reaches 7.45, it goes colourless again. Now it's going to become slightly alkaline. You can see that the pH now is about 7.82 and slightly pink. Now let's add an excess of our sodium hydroxide. So the pink tinge about 7.82. Let's add an excess of sodium hydroxide, and we can now see that the pH is going all the way up to 8. Now it's pink. So in a slight excess of hydroxide, the phenolphthalein is pink. We saw that there was a faint pink tinge about pH just over 8.2, and then it went properly pink at about pH 10. So it starts to change over a range of 2 pH units. So did the methyl orange. So it's important to note for an indicator to work in a titration, the pH range of the indicator's colour change must be within the pH change at the endpoint. And we know we can find the endpoint when we carry out pH titrations and plot a graph of pH versus the volume of the titrant. Both methyl orange and phenolphthalein make good indicators because they have distinct colours. Methyl orange, its colour change, remember, starts at 3.2 and ends at 4.4. And phenolphthaleine's colour change doesn't start till 8.2, and then its colour change is properly changed at pH 10. So the range in which they change is both around 1 to 2 pH units. Now, if we carry out a pH titration of a strong acid versus a strong base, say for example it's 0.1 molar hydrochloric acid, then the pH is going to start at 1. Remember, at equivalence, and we said that equivalence is when the hydrogen ion concentration exactly is equal to that of the hydroxide ion concentration. That is the equivalence point, but it's not the same as the end point of the indicator. This is a table of some common indicators from your caboodle textbook. So let's remind ourselves, methyl orange is red up until pH 4, in which it starts to change. So between pH 4 and pH 5, it goes from distinctly red to yellow. So the end point is an orange or peach colour. Phenolphthalein, however, doesn't start to change till about pH 8. So the change occurs between pH 8 till about 10.5. So the range for phenolphthalein is much higher. This graph here is the graph of pH against volume of base added. The pH ranges over which both phenolphthalein and methyl orange change colour are shown. To fulfil the first two criteria, the indicator must change within the vertical position of the pH curve. So either indicator will be suitable. Phenolphthalein is usually used because its colour change from colourless to pink is more clearly seen. This titration curve is one of a weak acid like ethanoic acid. You can see that the pH here starts at about almost 3 for a weak acid. And the methyl orange, you can see, is not suitable for a weak acid strong base titration because it doesn't change in the vertical portion of the curve. It's already yellow when you add the ethanoic acid. So it will change colour in the wrong place. You'll never actually see it go red. And over the addition of many cubic centimetres cubed of base, now phenolphthalein, however, with a weak acid, will change sharply at exactly 25 centimetres cubed of the equivalence point, and therefore phenolphthalein is a better choice of indicator for a weak acid strong base titration. Now let's look at an example of a strong acid weak base titration. So hydrochloric acid is a strong acid and ammonia is a weak base. So we can see from our titration curve it's a strong acid starting off at pH 1, and we can tell it's a weak base because the pH levels off just below 10. Now you can see at this point methyl orange changes over the vertical part of the pH curve, but phenolphthalein will be absolutely no use because it's still colourless here at the equivalence point. Finally, for a weak acid, weak base titration, like ethanoic acid and ammonia, neither indicator is suitable. There is hardly a vertical portion of the curve, and therefore methyl orange will have already become yellow and phenolphthalein will still be colourless. To summarise, therefore, phenolphthalein is useful when you have a strong acid and a strong base, and a weak acid and a strong base, but it's no good when you have a weak base. Methyl orange, on the other hand, is a useful indicator when you have a strong acid and a strong base, but not useful when you have a weak acid. Only when you have a strong acid and a weak base. Let's look at the question. So the question says, from the curves, choose a curve produced by the addition of ammonia to hydrochloric acid. So it must be one of the curves where a strong acid, which is hydrochloric acid, is in the beaker, and ammonia is a weak base. So that has to be curve C, strong acid, weak base. The next one is sodium hydroxide to 25 centimeters cubed of ethanoic acid. So ethanoic acid is a weak acid and sodium hydroxide is a strong base. So that has to be curve A. Finally, nitric acid to 25 centimeters cubed of potassium hydroxide. So this time the analyte is the potassium hydroxide, and the only curve which is starting off at a high pH is curve D. And as the potassium hydroxide is added, the pH drops suddenly, and you can see here that the nitric acid is probably about a pH concentration of about 0.01 moles per dm cubed. pH is ending off at 2. The next part of the question asks you to choose a suitable indicator. Let's read it carefully. So here is a table of acid-base indicators and the pH ranges in which the indicators change colour and their colours in acid and alkali are shown. Select from the table an indicator that could be used in the titration that produces curve B. So you can see that curve B has a large vertical point, and that means there are a lot of indicators that could be used in curve B. But it also says it cannot be used in the titration that produces curve A. The first indicator, tryptophan, actually changes between 1.3 and 3, and therefore it definitely can't be used to produce A. You can also see, however, in curve B that the pH is starting to change at pH 3, and tryptophan will have changed between 1 and 3, so it will already be yellow, and therefore the indicator of choice is bromocresol green, because that starts changing at 3.8, which is good for A. It starts changing here, so it's already yellow, and it's blue at pH 5.4. For curve A, it can't be used because it starts changing at 3.8, and by 5.4 it will already be blue. So the indicator is bromocresol green. The final question says give the colour change at the end point of the titration that produces curve D. And that's this time when we're starting off with a strong base and we're adding a weak acid to it. So it's going to start off with its colour in alkali, and we can see cresol purple starts off as purple when it's in alkali. Over the pH change, it's going to go from purple with excess alkali to yellow. So it's going to be a mix between purple going to yellow. So the end point is going to be yellow.